Good day, class. In this lesson, I will use a fictitious scenario to help describe how mathematicians have learned to calculate the average rate of change on the interval of a function, as well as the instantaneous rate of change at a specific point in time. So imagine a person traveling 60 miles per hour over a certain distance. So if we're talking about traveling 60 miles per hour, imagine we start at one location, maybe at home, and then we end on campus at our college classroom or something. And so we know we didn't travel 60 miles per hour all the way. So we're thinking about, well, what happened on an interval to sort of give us a better expression or a better representation of our travel, because remember that change is introduced, and this is the uniqueness that's found in our study of calculus. So that 60 miles per hour is not happening at all times, but we can sort of evaluate what's happening from a certain point of time to a different point in time. So we want to go back to the old school of distance equals rate times time. We remember distance equals rate times time, and we sort of get that. We've studied it, we've worked with it quite a bit, but this can sort of morph a little bit. So let's take a look at some alternatives. So here we're looking at just division by the time instead, so we can sort of isolate that rate. So now we see we've divided, instead of d equals rate times time, we now have r equals d over t, where we've divided both sides of our equation by t. So this is still a true statement where the rate equals distance over time. And now we're looking at, this is really, we can sort of describe it as the average speed, which equals to distance divided by time. And so I'm going to describe to you how we can sort of look at this as average speed if we play our cards right. So let's take a look. So imagine here on the left that rate, we're talking about speed at some specific time. It's approximately the distance that we've traveled over the time divided by time. But we have to sort of zoom in a little bit. We have to hold tight to what we mean by each of these elements of our approximation here. So let's look carefully. We're still dealing with that d equals rt, but we've just sort of adjusted it a little bit. On the left, we have speed at some time is approximately the distance at a certain time minus the distance at a different time, all divided by the time we've spent traveling. So notice in the numerator, we have on the right hand side of our approximation here, we have the distance of our second time minus the distance of our initial time is sort of what we're dealing with. And so we continue to sort of morph this thing. Nothing has really changed here. At this moment, we're just talking about abbreviating. So instead of writing out distance, notice how I'm just using that d of at a certain time. So d at my time 2 minus d at my time 1. If I subtract those out and divide that by my time, I'm really looking at my speed at whatever time is in question. So a lot going on there. So let's do some specifics here. We're talking about the average speed, maybe in miles per hour. So speed at 2 o'clock is approximately how the distance we traveled starting from 2 o'clock to 2:05. So between that 5-minute time interval, and then in our denominator, we're looking at that 5-minute spread of time. So notice how we can approximate our speed at 2 o'clock by sort of dealing with this same d equals r over t. D equals r times t. This distance formula, the formula that we're familiar with. We can look at this in sort of a different way. And so now we're describing speed at 2 o'clock is approximately the distance at 2:05 we've traveled minus the distance we traveled at 2 o'clock, all divided by 5, and so we can approximate how fast we're traveling. But remember, we've been studying limits. We're talking about limits, so we can sort of practice getting closer, a better approximation. So take a look. Now we're looking at a shorter interval of time. We're now looking at from 2:04 to 2 o'clock, or from 2 o'clock to 2:04, if you will allow that. And so this time interval is a little smaller. We're getting a better approximation. We can continue to improve upon our approximation by getting a shorter and shorter interval of time, yet still respecting D equals RT. And so we're getting closer and closer, and notice how that obviously we're going from 2 o'clock to 2:02 now. We're going to go down to 2:01, and at this point maybe we can sort of look at some milliseconds, nanoseconds, or something like that, but we can get infinitely closer and closer, and we're getting closer and closer such that eventually we would reach a time change of 0. No change in time in that denominator, which we don't want that. We can never actually get there. So we need to somehow represent, we'll never get to a time change of 0, but we can get infinitely closer to getting smaller and smaller, achieving smaller and smaller intervals of time without reaching 0, because obviously reaching 0 creates a problem. And so with that, we sort of describe that issue, not quite getting to 0, but getting infinitely closer. And so now we're back to dealing with the limit, as we spoke about in a previous lecture. And so here we still have our D equals RT. It's morphed quite a bit, we can see here, but we're describing getting closer and closer to that time change of 0, and so we want to describe that algebraically as the limit as the change in time approaches 0. So that change in x is getting closer and closer to 0, or getting closer and closer to no change at all. And then we have the difference in our distances in the numerator at specific times, and then that amount of time we spent in our denominator. So then we sort of, instead of writing out all those words, we know that mathematicians actually use notation. And so we're looking at a more respectable notation here. We have the limit as the change in x is getting closer and closer to 0 of our the difference in our distances. Notice my first term is talking about that initial distance plus whatever extra distance. Remember, we were dealing with the 2 o'clock, and so maybe that could have been up to 2:05, and that change keeps creeping down, down, down. So in our first term in our numerator, we're talking about our initial point in time plus whatever change, and then we're subtracting to get that difference, the initial point in time, the distance at the initial point in time. And so this is all divided by the change in x. And so also in the world of calculus, we sort of deal with the change in x being represented by an h. And so you'll often see the limit as h approaches 0 of our function at a given time, or plus some change minus that function at a given time, all divided by the change that's happening in time. And then this is what we'll use to represent our average rate of change. In a next instructional video, I will describe how you can observe the average rate of change on a given interval, which is what we sort of defined here, and then from there we sort of fall over into identifying the instantaneous velocity, at an exact point. So we'll take a look at that in the next lecture.